Okay, good everyone. So you are welcome to this week's class on scientific computing with Python. So today we'll talk about derivatives in Python. How do you find derivatives in Python? So there are like three approaches to evaluate derivatives in Python. The first approach is using numerical methods. Okay, numerical methods like the finite difference method. So usually if you want to evaluate the derivative of a function, the definition is that let's say the function is f. So the x is limit of x tends to 0, f of x plus h minus f of x over h. But in practice, there are many numerical methods that have been introduced, such as the finite difference methods, like the forward difference approximation, the backward difference approximation, the central difference approximations, and so on and so forth. All these are for first derivatives. Now, so the first forward difference approximation is written as f prime of x equals f of x plus h minus f of x over h, which is like from the definition of derivative. Okay, derivative of a function. This that's the order of accuracy of the code of the numerical method of the approximation being used. So for example, here is accurate up to order h, which is not so good. So there are methods that are accurate up to order h square. That is, this h is the spacing between the data, okay, like with this x in this case. So if the spacing is small, then this method will be more accurate. So the smaller the value of h, usually, okay, the more accurate will be the evaluation of the derivative. But of course, if h is too small, then it will result into round-off error. So you have to balance the value of h to use. It must not be too small and it must not be too large. Let's start from a simple example. Let's say f equals 2x raised to the power 4. I want to find the derivative of f, that is f prime of x. F prime of x means the f dx. I want to evaluate this derivative at x equals 2. Now, the analytical answer from our derivative, from the knowledge of differentiation, if you have f equals to x raised to the power 4, then f prime of x will be, it will be 4 times 2, that will be 8, then 4 minus 1, so that will be 3. So it is 8x raised to the power 3. Then at x equals 2, it will be 2 raised to the power 3, which is 8 times 8, 64. So the exact answer is 64. So usually if one is introducing a numerical method, so you have to compare that numerical method with some exact results, okay, before you apply that numerical method to other technical problems. So how do we implement this first forward difference approximation in Python? Very, very simple. Let's call the function. Let's create a function to evaluate this formula. Let's call it FD. That is first difference approximation. It will take in the function I want to differentiate. It will take in the x values. Then it will take in the spacing. Okay, and we return. Look at the return. So sorry, let me increase. It will return f of x plus h minus f of x divided by h, as it is written here. As it is written, that's what it is going to return. But make sure you put this bracket here and here. Otherwise, if you forget this bracket, it will be f of x plus h minus f of x over h. It means the code will first evaluate f of x over h before subtracting it from f of x plus h. But our idea, what we have in mind, is that it should first evaluate f of x plus h, subtract f of x, then divide the result by h. So you must be careful to use this parenthesis here and this one, okay, otherwise there will be error in your results. So the function I want to differentiate, let's create a function for that. The function is 2x raised to the power 4, so f1 2x raised to the power 4. Now, using the forward difference approximation, we said it will take in the function I want to differentiate. The function here is f1. The x, that is the value of x that I want to evaluate the function at, here it is 2. Then the spacing here, we are saying we're using 1 exponential minus 6. Okay, Now, so if we evaluate that and we print our answer, we compare with the exact value and the error. So if you run, our answer will go 64.000048 and so on. The exact answer is 64 and the error is minus 4.8 times 10 power minus 5. So it means this result is not so bad for this simple differentiation. Okay. Now we also have another formula called backward difference approximation. Instead of f of x plus h minus f of x, it is now f of x minus f of x minus h over h. Again, we implement it in Python. We create a function, we call it BDA, meaning backward difference approximation, and we write f of x minus f of x minus h, everything divided by h. Okay. Now again, if you apply the method to the function that we differentiated here, we got 63.999951994 and so on, and the error is also 4.8 minus 5. So the error is the same error as we got for forward difference approximation. So it's of the order of times 10 power minus 5. What about the central difference approximation? This is a more robust method. It's more accurate, and you can see it is the order is of h squared. So it is more accurate than the backward difference, which is of order h, and the forward difference, which is also of order h. Okay, so it is more accurate, this central difference approximation. It is more accurate. So again, let's implement this central difference approximation in Python. It will be f of x plus h over 2 minus f of x minus h over 2, everything divided by h. Now if you apply it to the same problem of 2x raised to the power 4, if you run, you get 64.00000894, and the error is times 10 to the power minus 9. So it means our result is now accurate. Okay, you know, I told you that here the error is of order h square instead of order h for forward difference and backward difference. Is now of order h square, so it is more accurate. So what does this mean? It means if you want to evaluate the derivative of a function, a more accurate method is to use the first central difference approximation. It is more accurate than the first forward difference approximation and the first backward difference approximation. I hope that is clear. So there are examples that I gave here. You can study them. Now, what about second derivative? Second derivative. So here we'll go straight to the first central difference approximation for second derivative, because we know that it is more accurate than forward difference and backward difference. Okay, so for the second derivative, the formula is given as this f prime prime of x. That's second derivative. That is d square f dx squared. Again, so you code it in Python. So f of x plus h over 2 plus f of x minus h over 2 minus 2 times f of x. Then this is the numerator, this is the denominator. Then we'll multiply everything by 4. So 4 times numerator divided by denominator. Okay, or you can, if you like, you can write it as a single code, as a single line of code. Just say result return 4 times blah 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 blah, like this. It's okay. Okay, but I use this method so that it will be easier for you guys to follow, and so as to avoid, because some students, they will forget this bracket here. If you forget this bracket, then there is problem. So there will be error in the result. So let's evaluate the second derivative of 2x raised to the power 4 at x equals 2 again, as at x equals 2. So the analytical answer is that f prime prime of x, you know, the f prime of x is 8x raised to the power 3. So f prime prime will be 8 times 3, which is 24, then 3 minus 1, so x squared. And if you evaluate it at x equals 2, it will be 2 squared 4, then 4 times 24, so you have 96. Okay, so if you implement the second derivative using the central difference approximation and you apply it to this problem, you get the analytical result is 96 and your numerical result is 95.99965. So the error is 3.4 times 10 to the power minus 6. Okay, so that's about that. So that's about first derivative and second derivative. So in exam, I can give you the formula for third derivative, and I'll ask you to find the third derivative of a function. Okay, so it's very, very easy to do. Just look at the function, implement it in Python, then apply it to the function you are asked to find the derivative. So it's as simple as that. Now, NumPy has a function called gradient that can be used to find the derivative of a function. Now, if you look at what we have done here, we have evaluated the derivative at certain x. It's not compulsory. Okay, you can evaluate it at different values of x. Make it maybe from x equals 0 to 20. Of course, if you use NumPy A range, so in this code, where is it? So here at xd, xd is set to 2 here. Yeah, this is xd equals to 2. So you can create an array, a NumPy array, so that you have different values of x to evaluate the derivative, and you get your result. Okay, so it's very, very straightforward to implement. Now, Python has NumPy, to be specific, has a function called gradient that can be used to find the derivative of a function. So let's say you want to find the derivative of x squared, or let's even use, we have been using 2x raised to power 4. So let me change it to 2x raised to power 4, 2 times x raised to power 4. Okay, so the exact answer is 8x raised to power 3, 8x raised to power 3. Okay, so I will now use NumPy gradient. So the NumPy gradient, it takes in two values. It takes in the y data, but it's in data form, not function. Okay, the data we have said, maybe we can say y equals maybe 1 to 10, and the spacing is 100. Okay, lean space. Lean space, this 1 is the starting point, this 10 is the end point where the number will stop, and the third number is the number of points that you want. So in this case, we need 100 points, 100 data points between 1 and 10. Okay, so the h is the spacing. The spacing can be x2 minus x1, or x3 minus x2, or x1 minus x0. That is, the nth number minus the n minus 1th number. That is what we mean by the spacing. Okay, so the exact answer is 8 times x raised to power 3. So in Python, we just called gradient y comma h. Okay, now so I'm going to plot this graph of y prime and the exact. The exact is 8 times x raised to power 3. Okay, so we have learned how to plot graph earlier. So you can see it beautifully describes the data point, the derivative. Okay, so the numerical and the derivative, they are on the same line. But if you use 10 data points, let's say, you can see there's a problem here. Okay, so the more points you use, the more accurate will be your results. So let me use 100 so that it will be more accurate. In fact, if I use 1000 data points, it will even be more accurate, okay, than 100. So that is about that. So this n, because if you look at it, when I used 100, it's good from here up to this point, but when you get to this point, there is a small disparity. Okay, so but if you change it to maybe 1500 points, it will improve the accuracy. Okay, so you can see that the numerical method and the exact method are on the same line. They're on the same line. So it means this method is good for evaluating numerical derivative. Okay, another example. Let's say we have y equals sine x. So and x is from 0 to 2 pi, 100 data points. So again, h is x. It can be x1 minus x0. It can be x4 minus x3, or it can be x10 minus x9. Okay, minus x9. Okay, but I'm just using x1 minus x0 so that I pick the first point and the second data point. Again, so the exact, if you differentiate sine x, what's the answer? The answer is what? Cos x. So if you plot this, this is what you obtain. So numerical and exact. So again, this is good. So again, this is 100 data points. So let's change it to 10 data point and see. You can see the 10 data point is not too good. The numerical does not follow the exact. So it means anytime you are using a numerical approach to do differentiation, make sure you have enough data points. Okay, the more data points you have, the more accurate will be your results. I hope that is clear. Okay, now so we have looked at how to evaluate derivative using numerical methods like the first difference approximation, first forward difference approximation, first backward difference approximation, central difference approximation, and we also looked at how to find second derivative. Okay, then we went on to look at a numpy function called gradient to evaluate the derivative of a function, usually a data. The function will be in data form. We can also analytically evaluate the derivative of a function using SymPy. SymPy is another Python mode called symbolic Python. NumPy means numerical Python. Okay, we use NumPy a lot in science and engineering. SymPy is not often used. Okay, why? Because SymPy deals with symbols. Okay, but usually in science and engineering we deal with numerical data. But just for completeness, I will show a simple example of how to use SymPy to find the derivative of a function. So let's import SymPy as SP. Then x is, so we have to, so the x, or the function that I want to do the derivative with respect to, let's say x, we'll first have to put it in symbol form. So we say, let me use from SP import symbol. Okay, so I just use symbols. Okay, then also import sign and import diff. Okay, so that I use them straight. Yeah, it's okay, but I'll explain something later. So x equals symbols x, that is, we have symbolized x. Then f equals sign x. So f prime, that is, we want to differentiate f. So we say diff. The function is what? Diff. That's differentiate. Differentiate f with respect to x and print. So the answer is going to be what? Cos. From SymPy. So the answer is cos x. Okay, and if you put cos, let's import cos as well. If you want to differentiate cos x, what should be the answer? What will be the answer? Derivative of cos x with respect to x is going to be what? Minus sine x. Okay, minus sine x, so on and so forth. So that's how you do derivative of a function in using SymPy. So this one is symbolic. Okay, all right, so this is where we stop. You can read more in some of the recommended textbooks. Okay, some of the textbooks that are recommended, you can read more about numerical derivatives in Python. Okay, so we'll stop here for now. So see you. So the next lecture will be on integration. All right, see you later.